Welcome to Conversations with Tenzin. I'm doing this podcast because I meet a lot of interesting, a lot of wonderful, a lot of dedicated people on campus and in my life. So today in this episode, I have my very good friend Ufuk.
Hi.
And yeah, welcome. Welcome to the podcast.
Thank you. Thank you for inviting me this.
Okay, Ufuk, so I'm going to start by asking what has been your story till now? What was your journey from your home to getting to MIT? So can you share about that?
All right. So I am born and raised in Turkey, and my parents were both teachers.
Are you from Istanbul?
I am from Samsun, which you probably have never heard of.
Yes, we only hear Istanbul.
Yeah, like Istanbul, Izmir, Ankara, Antalya are the touristic attractions, and they are awesome cities. And Samsun is also an awesome city, but it's not popularly known right now.
Okay.
It's on the Black Sea region, the north of Turkey, at the middle. And that's where I raised and born. My parents are teachers, both teachers, and I have a twin brother that we grown up together. And in Turkey, I went to college, which is called Bilkent University, which is one of the prestigious universities in Turkey. And I studied electrical electronics engineering and physics as double major. And after completing this degree, I was applying to Ph.D. In different universities, including US universities too. And to be honest, I wouldn't have this kind of vision if I wouldn't have my friends, because we were about 12, 13 friends group that were dedicated to do research, study, and make something different. And we had this aim to also continue and pursue our degrees in masters, in PhD at universities in US. So we were actually applying it our last year. So what I wanted to work was always something that is evolving, because when I first came to universities, you don't have any clue what kind of path you will follow, and what is your passion, and what do you want to do. So that was taking my time, but I was always doing research. I was applying to summer research programs in Turkey, or I also applied one in Switzerland at EPFL. And I was always doing research with professors about different kind of topics. That one was ultrafast lasers and optics, and other one was going into machine learning. And I just wanted to find my way out of it. And at the end, like over the 4.5 years in Bilkent University, I started kind of concluded that I wanted to do quantum mechanical.
Yes, this is your research right now.
Research that involves actually both electrical electronics and the physics research actually. So what I'm doing right now is quantum information science, and this is what I applied to the universities for. What we were doing is to look for the professors that actually is doing research on this, and if I found them, I would put it in my spreadsheet, and then I would send them emails, like to see who is gonna want to take me there. And I applied to 10 universities, about 10 universities, and then I got into MIT.
Okay, was MIT your first choice?
MIT was my first choice.
Okay.
Yes, like I also applied to other universities, but like MIT is one of the universities that actually admitted me.
Okay.
And so when I came here, what I wanted to do was just an abstract view of like quantum information science. I was not familiar with the whole field, but as I progressed through the literature, read the literature papers, then I get the sense of what it is.
So I wanted to ask, sorry for interrupting, but I wanted to ask, what was your first research about, and how did it end up to quantum, your interest in quantum?
Yes.
How did you start your research field? What was your first question that you started with, and how did you end up in quantum?
Actually, in my preparation years of Bilkent University, which I was just taking English courses, actually, I was reading this book written by Jim Al-Khalili, and it's called The Quantum on the Edge.
Quantum on the Edge?
Yes.
Okay.
And it actually basically talks about how quantum mechanics can be a potential answer to the questions on biology that we don't know the quite answer. For example, there are birds that actually uses Earth's magnetic field to navigate, but Earth's magnetic field is so weak, and there is a question that how they can sense this very weak
force
signal.
Yeah.
Right? It's basically a signal, and one of the questions that, like, one of the answers that are coming up with is in the book is you can use entanglement structure.
Yeah, so that is another interesting theory that yes, entanglement.
Or like generally superposition, entanglement, and measurement is those three sets of things that you can harness in quantum information science. And this was what these three key ingredients is what they were using throughout whole book. And this actually gave me a very good sense that I actually want to pursue this field. It seems to me that it's actually very interesting. So I had this idea that I want to work about quantum mechanics on the applications. And this I had this my idea throughout 4 years, and I wanted to actually pursue on this field. And I actually like, because my there's limited resources on or professors on actually working on this field, I actually wanted to also research on different fields that might be connected to it. So what I did was first ultrafast laser and optics, which was a very interesting field. And my professor's name was Ömer İlday. He was a professor in Bilkent University, and he was a great supervisor to me throughout all my undergraduate life. And then, because this project, these ideas of him actually wanted me to pursue the research more. And one of the other research that I was doing was in Koç University in a summer research program. I was working on machine learning, deep learning models that I was coding basically and testing through data to give the sense of like one kind of a specific model of neural networks, which is called spiking neural networks. And at another research that I was done was in EPFL, which was in quantum measurements. Yeah, it's in Switzerland. It's located in Lausanne, and it's one of the prestigious universities in Switzerland as well. And in that lab, I actually get the sense of what those quantum people are doing in experimental manner. And this also gave me the sense that this is still an interesting research. So I actually should pursue this. And that's what led me to quantum information science.
Nice.
Actually.
So you saw the potential.
Yes, I saw the potential, but not just the potential, but it was interesting to me. It was something that I might put my mind on puzzling questions and ideas.
So my next question is, when young students think about getting into MIT, they think, oh, it's a place for all the very smart people. I cannot do it. So what are the things you're going to tell the young people who, like in schools back home in our country? What would you advise? Like, how do they get to a place like MIT? Get into a place like MIT?
I think they should know that everything is actually like in admission process. It's actually about luck as well, because like you can't just apply to one university and then expect to get accepted, because sometimes like there are a lot of applicants on the department that you are actually applying to, and you can't actually expect everyone to actually rank everyone in a like
Order.
like
In order.
or in an exact order right
Yes.
now, so there's actually a like unlucky group of people that actually got unaccepted not because of a good reason. That's just natural, because there are a lot of applicants. And because of that, actually, first, luck is important. Two, you shouldn't put yourself on an statistic. Every individual could be an outlier in statistics, because statistics are about when you have large group of people and then you just want to observe the behavior of the large groups. But one person could not be in this statistics because of that. So don't just think that, oh, those are smart people, those are very beyond me. This is not true. First of all, like not everyone here is genius. Not everyone like here is like the perfect person. Everyone and there is always this syndrome, which is the imposter syndrome.
Yes.
In students of MIT, like everyone thinks that they are not actually worth of being at MIT, and they are like accidentally here.
Everybody thinks I'm smart, but why am I not smart?
Yeah, like they are thinking this, but this is actually not true. You shouldn't think that way. So first one, luck. Second one, you shouldn't put you on a statistic. Third one, nobody is genius here, smart here. Like they are smart, but they are not the perfect like prodigies.
Excellent.
And this is the third thing I would. Those three things are main things that they should consider. They should just apply no matter what, because if you don't.
Try.
If you don't try, you will have the regret of not doing it and the thinking of, oh, maybe potentially I would be here if I would apply.
Okay.
But if you apply and you get, for example, maybe rejected, then you don't have any, like you have peace on your mind.
Yeah, you don't
I
have
tried
regrets.
and I failed, and this is all.
And I'm going to try again.
I tried my best and I can try again. So what you should do is to apply many universities that and then just see what goes on, because as I said, it's luck. Like you might just be unfairly dismissed on the admission in one university, but if you actually apply to many universities, then this chance is low.
I think this is a great message for any student.
Yeah, exactly.
To keep trying, and if you get rejected, just keep on trying. I mean, if you don't try, then you never know, right? And you live with the regret.
True. And if you are rejected from Harvard or MIT, that doesn't mean that you were not qualified for it.
Yes.
That's one of the main points.
So coming back to now, what is happening now, because you're doing this amazing research on quantum field. So I want you to talk about a little of what you're doing right now, working on right now.
Yeah. So current technologies we have that is embedded in our whole life, telephones, communication systems, computers, they all have some basis of physical set that their works and functionality are based on. And for example, for computers, you can say about transistors, which actually use currents and electrical machinery, the semiconductors, for example, to encode the bits that are the computational basis,
or traditional
informational
binary
base as like 0 and 1. This is what we call as what I group as classical technologies, and what we are trying to do is to our field of work I will call as quantum technologies. And what quantum technologies differ is that you can actually use subatomic particles, which actually are governed by the quantum mechanical laws on nature, to actually work for you, work for your technologies. They can actually help you to make computations or specific things very efficiently. And this actually comes from exploiting the quantum mechanical phenomena like entanglement, superposition, and the quantum measurements. Those three ingredients actually makes this difference, and one of the things that are actually should be our interest is entanglement, which is actually the thing that is actually blows the minds out when it was coming in the physics era of quantum mechanics. And entanglement is basically this: it's the perfect correlation among pairs despite very large distances. For example, think of two subatomic particles, for example, electron. Electron have a quantum mechanical property which is called spin. And you can think of spin as could be spin up and spin down.
In random direction.
Yeah, like it could be in random direction too, but for the for convenience, I would just say electron could be in spin up and spin down. And if two electrons are entangled with each other, if you measure one of the electrons' spin, and it directly and instantly affects the state of the other electron. This is the promise of the entanglement. For example, if you measure spin up on the electron, then depends on how it's entangled, the electron will instantly come to the
so it means the
spin
electron
down.
have an influence on the other electron.
Exactly.
That's why you call it spooky.
That's true. As you may say in public opinion, like you can measure one thing and it directly instantly affects the other one. And this could be it at any distance. It's not actually bounded by any distance in theoretical level.
Is there a proportionality of the magnitude with the distance?
Actually, like if we go into detail, there's fidelity measure. Like your pairs might not be perfectly entangled, but I'm just assuming ideal conditions where there's perfect entanglement. And if we have been maintaining this perfect entanglement in between two electrons, this means that if one of the electrons is here and the other electron is like at the edge of the universe,
oh my God,
you can just directly influence the other electron by just measuring your electron. This is what Einstein also called as spooky action at a distance. This is actually like the ones that we can actually harness in quantum technologies. For example, there are radars that are emitting light into one of the targets, and when it actually reflects from the target, it comes to you. You can say that there's a target over there. And this has a precision because like on the medium there are a lot of things that might occur, like pressure, wind, dispersion of the light. So you don't always have a definite precision. There is always some kind of margin of error.
Yes.
And what quantum technologies or quantum information science in an umbrella term does is that to increase this precision by using this entanglement. So we want to decrease this margin error by harnessing the subatomic particles or quantum systems that displays this entanglement or superposition structures. And this is, for example, can lead to quantum radars, where we actually not just send a light, but we send a light that is entangled to the one of the lights that we actually keep on ourselves. And when it comes back, we just look at the correlation.
Yes.
Because they are correlated in some way, and we should be able to actually use this correlation to infer something more.
Oh, okay. Interesting.
And this is like applied to other kind of technologies which we call as in the umbrella term quantum information science. For example, there are computers, and I think everyone is now heard of quantum computers. And this is actually amazing too. It can have a lot of aspects. For example, in factorization algorithm. For example, let's say we have this number 21 and we want to factorize this on like 3 times 7. And if you have a large number of this in classical computers, classical computation, classical algorithms, you don't have an efficient algorithm that actually factorizes a large number. But in one of the papers, Peter Shor, who is one of the leader on this side, like leading researcher on this research, actually showed that if you have a quantum computer, you can use quantum mechanical law to make a more efficient algorithm of factorization just with quantum computers, which was an amazing result actually for the computer science people as well. And this is one thing. This is the quantum computer side, and IBM, like the IBM, Google, Amazon, like and a lot of startups in quantum are actually trying to progress this quantum research so well that we can actually implement these algorithms in a real setting.
Oh, okay.
And that's what this is an industry right now that is actually invested a lot and has a lot of aspects. Quantum computing is one thing. Quantum, for example, there is a field of quantum sensing as well. For example, you can with interferometers. For example, the Mach-Zehnder interferometry that like just uses to the phase differences between the two lights coming out. Actually, LIGO, they use this similar structure, like almost the same structure, like same logic. The LIGO, they are using this kind of like same logic to actually detect the gravitational waves, because when there's gravitational waves, there are ripples in the space-time that actually is a signal that affects one of the lights coming, and the other one is actually kept in the laboratory. So if there's a phase difference, you can actually see that on the screen. And that kind of ripple, which I will call as signal, is the one that we want to measure precisely. Because if it is very small, then our classical tools might not be able to detect it.
Yes.
But if we can use quantum resources, like which they use quantum light, squeeze light, as one of the research on the quantum sensing, then they kind of show that they have actually much more precision on sensing signals present in the surroundings.
So if I understand everything and try to put it in a simple term, so what you're trying to do is there is a ghost and you're trying to build a tool to detect that ghost.
Electrical engineers would call it signal.
Yeah.
We call it signal because that's our term.
Thank you so much, and I wish you all the best. I know you're going to do some amazing work down the line, and I
Thank
won't
you.
be surprised, if I have to look back to this video and say, oh, I know this guy who is winning the Nobel Peace Prize in physics.
Oh, well, that would be a great honor.
So there's a lot of potential, and I wish you all the best. And to end this podcast, I want to ask this question about, you're always working hard and you keep yourself going. So what motivates you in life? What is the source of motivation?
Well, my source of motivation, well, it's because it's interesting, and that's the driving force.
So you're
Actually, I
interested.
always want to do my best, and I want to keep going on, working on what's interesting to me, and that's actually a great way to pursue for me. And it actually also gives my salary too. But
so first is interest, second you want to give your best, and third is salary.
Exactly. That's what I'm paying for, right? But of course, well, I would also take another job if I wanted, but I just didn't want to because this is a great way that I think is a great way to pursue, and I like research.
I think you're one of the lucky few where you're getting paid to do something that is of interest to you.
Well,
And that's why you want to give your best. So I'm just
right? Yeah, exactly.
trying to put the three together.
Yeah,
So if you're paid and if you're not doing something that you're not interested in, you not give your best.
that's true. That's true, actually.
Yeah. So I wish you all the best. Thank you so much for giving me the time today.
Thank you for inviting me. Actually, I didn't know that I could do that kind of interview.
You can also look back to this podcast after 5 years or 10 years and see, oh, this is what I was doing. Now I've achieved it.
Or I would say, oh, I did say this wrong. Maybe I would do it better,
Yes, there's always room for improvement.
Yeah, that's true.
That's what we do. We keep improving ourselves every day.
That's a great idea, I really appreciate that.
Thank you.
As you said, actually every person is a world, right? So every person has something to say, something that is interesting,
Yes.
that they can say.
Every person that I see walking, I see them as a journey, a journey that person has taken. So it's really amazing. I mean, what they have gone through to be where they are, and the stories of struggles, the story of triumph, the story of failure, tears, laughter.
Yeah.
This is just all there in one person.
And I think as much as that person is also of significance, what actually give them push are also of significance. My parents that actually raised me and gave me the motivation to pursue such things, the education, and my friends that actually gave me push to go for this academy that we actually did together, they are the significant
Yes.
people in my life that actually helped me.
We cannot do it without our family. Family is the most important support. So thank you for listening to Conversation with Tenzin. I had Ufuk here today, and we had this wonderful conversation about his research, about his story. So this is the reason why I'm doing this podcast. I meet a lot of interesting people, amazing people on campus and in my life. So I want to capture these stories and not forget about these stories, especially the stories. So this is the reason why I'm doing this podcast. So thank you so much for listening to that Conversation with Tenzin.
And thank you, Tenzin, for everything.
Thank you.